Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you. And as you know, this is the DADM 2, which is Data Analysis and Decision Making 2 course under NPTEL MOOC series. And this total course duration is 30 hours, which is for 12 weeks. Each week we have 5 lectures, each being for half an hour. And as you know that after each week we have one assignment. So, in totality we will have 12 assignments and the final examination. And as you can see in the slide, this is the 15th lecture, which is the end of the 3rd week. So, if you remember, we are considering the different types of return to scale, decreasing return to scale, increasing return to scale, then constant return to scale. So, continuing the discussion, let us consider the increasing return to scale, but now with the input being measured along the y axis and the output being measured along the x axis. So, if you have that, your graph would be as shown, where if you consider, say for example, this only one issue is that this blue line which I have drawn horizontally onto the left is too close to the x axis. So, you may not be able to differentiate, but actually whatever I have discussed for the decreasing return to scale and increase all the 3 different graphs. One was with input was in the x axis, output in the y axis, and in the other case input was in the y axis and output was in the x axis. Then we had the combination, then that was basically for the decreasing return to scale. Now for the increasing return to scale, again we will have the same combinations, input once being drawn on the x axis and the next instant being drawn in the y axis, and then we will come to the constant return to scale. So, in this case, if you consider any DMU which is inefficient, which is where I am hovering my stylus or this electronic pen. So, obviously there can be 3 different situations. One, for the same level of output, what I can do is that, because if it is an increasing return to scale, I would basically technically try to go up, which is not right, because in that case you will be increasing the input and maintaining the same level of output, which is not possible. Obviously, I will not do that. It is possible, but I will not do that. In the second case, we will consider that we go horizontally onto the left, that means at the same level of input we decrease the output, and we have the DMUs as shown as the pink and the blue one, the pink one being for the case when is efficient on the efficient frontier, and then the blue one being again the DMU which is efficient on the efficient frontier. Another concept can be where you go diagonally, that means you are trying to increase decrease both the input and the output. So, obviously in this case we will try to take in the increasing return to scale, we will try to basically decrease the output, but maintaining the same level of input such that our efficiency increases. Now, consider the constant return to scale. So, in the constant return to scale, obviously it is a straight line with respect to input or output being drawn on the x axis or y axis, whichever it is. So, in this case we have output along the y axis, input along the x axis. If you reverse the diagram in the sense that you have input along the y axis and output along the x axis, the graph would all be straight. It means, in the sense, it means that for 1 unit increase in the input, the output also increases in the same way, such that the constant return to scale is maintained. So, in this case, if you have a DMU which is inefficient, so in this case the DMU can go either vertically up, horizontally onto the left or right, depending on which type of diagram you are looking at. That means output on the y axis or input on the y axis. You can go horizontally onto the left or horizontally onto the right, or in the case you can either go vertically up or vertically down, depending on how you want to reach the efficient frontier. So, obviously in this case you will concentrate on either the input and the output to maintain your same efficiency. Now, consider the case for changing return to scale, where the return to scale varies. So, in this case you have the diagram is like this, where you have the graph, and here remember I am measuring the input along the y axis, output along the x axis, and my actual graph is like this. So, one set is decreasing, another set is increasing. So, if you see the DMU which is inefficient, where I am hovering my stylus, So it can either go horizontally onto the right, horizontally onto the left, which are the blue lines, or you can come vertically down. So there are two graphs, but they are almost similar, they overlap each other, so you are seeing only one pink line. And another can be, you can go radially such that you go take the least distance and reach the curve, which is basically 90 degrees at the point, which is the tangent. So it can either go on to the left bottom corner, another can be on the right bottom corner. So obviously when you take the green line, then you are trying to basically maintain a proportion of the input output in order to basically increase the efficiency. While if you go horizontally onto the right or the left, you are basically trying to concentrate on maintaining a same level of input, but trying to basically increase the or decreasing the output depending on how the things are. So if it is a decreasing return to scale, so obviously maintaining the same input, you will definitely try to decrease the output such that your efficiency increase. In the other case, when it is increasing return to scale, you will try to just reverse the situation. Now we will consider the actual optimization problem and come back to the solution of that later on, how you solve it. So consider that what we mean by efficiency. When we are talking about efficiency, we always talk about the ratio of the output to the input. And when we are talking of the efficiency, actually we will try to maximize the efficiency. So if there are different type of DMUs, we will try to basically maximize them and put from the highest to the lowest, such that the ranking would be easy, so we can compare them. Now another picture can be, which I will come later on to the solution or to the formulation. Let me use the word formulation. Another can be that why not basically consider the ratio of the efficiency, that means the ratio of the input to the output, and they basically try to rank them from the lowest to the highest, such that if I rank them from the highest to the lowest considering the output to the input, I should technically get the same type of result. So these are the two approaches which I am going to follow, or which we will follow. Now consider that it's an output oriented model considering the kth DMU. K is that small k, so obviously small k ranges from 1, 2, 3, 4 till capital K. So obviously I am taking in arbitrarily any DMU for our consideration. Now it is an output oriented model, so obviously the emphasis would be on the output as such, and I will discuss that how it can be done. So consider the efficiency of that kth DMU. So if I consider the efficiency of the kth DMU, the ratio would be, what is the ratio and what I want to do, I will discuss. So the ratio is basically the multiplication of the weights for the output multiplied by the output divided by the weights of the input multiplied by the input. That means I am taking the summation in the denominator. You will have the summation of all the V's into Y's for all the combinations of the output which you have for that kth DMU only kth, because we are not going to consider anything else. So if there are 10 DMUs, I am going to consider arbitrarily, say for example the fifth one, and once you understand that, then I will explain that how it can be extended for the first, second, third, fourth, sixth, seventh, eighth, ninth and 10th. It can be, fifth is just an arbitrary example, it could have been anything else also. So we will take the ratio of the sum. In the numerator you have the sum of the multiplication terms of which is basically the output and the output weights, which is Vjk multiplied by Yjk. Now here k is the DMU number and j is basically the subscript pertaining to the output only. Now in the denominator what we have the summation of Uik into Xik, where again k is the DMU number and I is the input based on which we are trying to consider. So if you want to maximize the ratio of the output to the input, what are the constraints? Now the constraints are very simple. So what we are trying to do, we are trying to maximize the efficiency of the kth DMU corresponding to the fact that the ratios of all the DMUs, ratios means the output to the input ratios of all the DMUs should always be bound with less than equal to 1. So what I am trying to do is that I am trying to increase the efficiency of the kth one, but at the same time trying to basically ensure that in the constraints the efficiency of all the other DMUs including the kth one are all less than equal to 1. So in the objective function we have the maximization one, and in the constraints we have the ratios of the output to the input, which is the efficiency, and all being less than equal to 1. Now let us look at this problem. If you look at this problem, this is a non-linear problem because this is a ratio. So I have to basically convert it into a simple linear optimization problem such that we are able to solve. So what do you do? So, before I go, let me again repeat it. You are taking the maximization of the ratio of the output to the input for the kth DMU, kth is arbitrary, and the such this constraints are all the efficiencies for all the capital K number of DMUs, where you are taking the ratio of the output to the input, and each ratio is basically less than equal to 1. Now, this I said is a nonlinear formulation, so I need to basically convert into a linear formulation. So, this is what I do. I take out the denominator in the objective function, forcefully put it as 1. So, that means I am pegging the input to a ratio of 1, and in that respect I am trying to increase the output. So, once I see the objective function, it now becomes maximization of the summation of Vjk into Yjk, where again J is basically the output number, K is the input number, and what happens to the constraints is what I am going to again discuss. So, the constraints are like this. The first one, if you remember, the first constraint was basically summation, which was less than equal to 1, was the summation of Vj1, because that is the first DMU, multiplied by Yj1, this is the first DMU, and J is, as you know, I am repeating it, is the output number, divided by summation of Ui1 into Xi1, which was less than equal to 1. So, what I do is that I take the denominator onto the right hand side and again bring it. So, now it becomes a simple less than equal to type constraints with no denominator. Then I bring the right hand side on the less than equal to sign, I bring it on the left hand side, and I do it repeatedly for all of them, apart from the last one, where last one means before the kth one, where I am basically trying to put that input bundle as equal to 1, because I am trying to maximize the output such that I am putting a restriction on the input, it should be 1. This is basically I am trying to rationalize it or normalize it. So, now actually when we started, we had basically k number of constraints, and the k number of constraints continues to remain the same, but in this case the constraints have taken a change. They are now placed in a different format, where all the k minus 1 constraints which are there, which does not consider the kth DMU, are of this form. What is this form? It is summation of Vj whatever the k DMU is, multiplied by Yj small k minus summation of Uik into Xik, that should be less than equal to 0, and the last kth constraint would be such that the ratio for the case when you are taking the input as 1 will be ensured. Now, what is the change we are having? The change we are having is that we are slowly trying to convert the nonlinear optimization problem into a linear optimization problem with the same number of constraints and same number of objective functions. So, objective function gets converted from a nonlinear ratio to linear ratio 0.1, and the constraints which are also nonlinear are slowly converted to linear constraint. For k minus 1, everything is less than equal to 0, and for the case when we put being the kth one, we are forcefully putting the input as 1. So, obviously now we have all linear constraints. Now, let us consider the input oriented model. So, in the input oriented model, what we do is that we try to maximize in the output oriented model, we have tried to maximize. Now, in the input oriented model, we will try to minimize. So, the minimize in the sense that we will try to minimize the ratio of the input to the output, and the constraints would be such that rather than trying to put them as less than equal to 0, we will try to basically put them as greater than equal to 0 and do the same conceptual fundamental change in the problem such that it gets converted from a non-linear problem to a linear problem. So, this is how I do. Objective function is minimization of the ratio of the input to the output. So, obviously in the input, which is the numerator, we have summation of Uik into Xik, and in the denominator, which would basically be for the output, we have summation of Vjk into Ijk. That is point 1. Point number 2, for the such that constraints, we will have all of them as greater than 1. So, what we have is basically again the ratios, but the ratios as they being greater than 1, what we are doing is that trying to take the ratio of the input to the output such that the input to output is definitely greater than 1, and we put it like this.
The first constraint is summation of ui1 into xi1 divided by vj1 into yj1, that is greater than 1. Similarly, for the second one, it is summation, in the numerator is summation ui2 into xi2 divided by vj2 into yj2, and continue it for the all number of k number of DMUs. Now again the question happens is, they are all non-linear objective function and non-linear constraints. So we need to basically convert them into a linear constraint and linear objective function. We do the same thing. Here now we want to minimize the input, because the input is an input oriented model, but keep the output value as 1. That means in the first case, when we took the output oriented model, we fixed the input at level 1 and try to basically push the objective function, which is the output, as far as possible, as high as possible. That was case 1. In the case 2, when we take the ratio of the input to the output, we basically put the output level as 1, normalize as 1, and try to basically push down input as low as possible, such that we get the greatest efficiency in both the cases. So now we basically have a minimization of summation of uik into xik, which is for the kth DMU, and the constraints are like this. The first constraint, so what you do is that you take the denominator for all the constraints to the right hand side, then you bring the right hand value to the left hand side, and hence it becomes greater than 0. So the equations are as follows, apart from the last one. I will come to the last one again in a similar way as we did for the output oriented model. The constraints are summation of ui1 into xi1, that is basically the bundle of inputs, minus summation of vji into yji, which is basically a bundle of outputs. So difference between them should be greater than 0, and we do it for all the DMUs apart from the kth one, because for the kth one we have ensured that the summation of vjk into yjk is equal to 1, because we are trying to minimize the bundle of inputs. That means, as I repeated, I will repeat again, in the first case we basically fixed the input and tried to push output as far as possible or as high as possible. In the second case, we fix the output and try to push down input as low as possible, in order to, in both the cases, try to maximize the efficiency. In the optimization formulation, for where both input and output are utilized, we will basically try to do a very simple, this is not the actual way how the DA is solved, but we will try to basically take a very different approach and try to take a multi-objective problem, where we try to maximize the bundle of, say for example, outputs and minimize the bundle of inputs which we take. So it can be maximization of one function and minimization on the other function, or it can be maximization of the output minus the input. This is because the minus sign with the maximization sign will basically make it a minimum one. So what would be the constraint? The constraints would be basically fixed both to the input and the output. So if I consider the optimum ratios of the maximum values of the inputs for each and every DMUs as I1 star, I2 star, I3 star till IK star. Similarly, for the outputs I have O1 star, O2 star, O3 star till OK star. So obviously these K values are the suffix, sorry. So I, when I mean I1, it basically I suffix 1 star is the maximum input I can utilize. Similarly, when I have O suffix 1 star is the maximum output which I can get from DMU 1. Similarly, the suffix changes depending on which DMU I am going to consider. So if you consider the input and the output, so it will be, I am not going to go into the details because the problems will be very similar when we solve it, and it will be kept simple. So what we ensure is that the bundle of the inputs for the ith one in DMU should be always less than equal to I1 star, and the bundle of outputs for the first DMU should always be greater than equal to, this is the objective functions we want to have, it will be greater than equal to O star, where I star or I values are the maximum input utilization and allowed for kth DMU, and the O star is the minimum output needed to or assured from the kth DMU. So thus technically the above set of problems considering both output, input and combination of input output models, each of which runs k number of such times identifying the relative scores of the DMUs, and thus in each set of simple linear optimization problem, because we have been able to convert this non-linear optimization problem using this transformation into a simple linear optimization problem. Thus in each of the simple linear programming model, each DMU tries to maximize the efficiency score by choosing a unique combination, using a unique combination of both input as well as output weights. Thus a DMU is considered efficient in case its scores is basically less than 1. If it is 1, it is efficient, but I will come to the efficiency concept later on, and else if the score is less than 1, obviously it is said to be inefficient. If it is equal to 1, we will call it an efficient one, but obviously efficient one would also have a different connotation, which I will come to that later. So let us consider few simple formulation problem. Let us consider an example and then proceed. Machine 1 produces 100 pieces of an item, say XYZ per hour, per day a shift of 8, and the input utilization is 10 units of raw materials and 2 units of labor. Machine 2, which is DMU 2, produces 80 pieces of the same item XYZ per day, and the input utilizations are 8 units of raw materials and 4 units of labor. Machine 3, which is DMU 3, produces 20 pieces of XYZ, and the input and the labor utilizations are 12 units of raw materials and 1.5 labor hours. So this is how we will formulate. So if you are told to find out the utilization on the machine considering the output oriented model, we would simply calculate the respective efficiency considering the output oriented model, where you put the output in the numerator and the input in the denominator and try to basically maximize that, while in the input oriented model we will try to put the ratio of the input to the output, fix the output at a level of 1. 1 is basically a normalization 1, and try to minimize the input. So for machine 1, obviously it will be maximization of V11 into 100, which is for the output, and the input you have, because there are two things, which is raw materials and labor. So they were basically 10 and 2. So it will be U11 into 10 plus U21 into 2, which will come into in the denominator. Such that constraints, obviously they would basically be on in the similar line. So the such that constraints would be now 3, because there are 3 DMUs, and they would be as follows. I will only first read the numerator and then read the denominator, and each of these 3 equations would be less than equal to 1, because you are now trying to do the output oriented model, where output will be increased subject to the constraint that subject to the idea that input would basically be fixed at a level of 1 unit, and you will try to increase the output as far as possible. So the constraints are, in the numerator is V11 into 100, while the corresponding denominator for the first equations would be U11 into 10 plus U21 into 2. So the second constraint numerator is V12 into, so this 1 and 2 I am repeating are in the suffix, V12 into 80, and the corresponding denominator is U12 into 8 plus U22 into 4. And the third constraint, the numerator is V13 into 120, and in the denominator you have U13 into 12 plus U23 into 1.5, and each of these constraints would basically be less than equal to 1. So and similarly, when I go the formulation for the second and the third, I will only concentrate initially on the objective function and then basically give a very general feedback about the constraints. So machine 2, the DMU 2, the maximization would be, this is a maximization problem, sorry, I should have repeated it, but I am sure you understand that, because this being an output oriented model, maximization would be V12 into 80, and in the numerator you have U12 into 8 plus U22 into 4, and the constraints remains exactly as they are, only remembering that when you convert this non-linear optimization problem to the linear optimization problem, be careful that for which of the constraints are you trying to basically put it at 1, because if it is the first optimization problem, then it will be corresponding to the first constraint. If it is the second optimization problem, it will be corresponding to the second constraint, so on and so forth. So as there are 3 DMUs, you will have basically 3 optimization problem, and you will basically do the changing of the constraint with respect to the first, second and the third. So we are going to just read the initial non-linear formulation simple case for the third DMU. We have already completed the first and the second. The third DMU will be maximization of V13 into 120, which is in the numerator, and in the denominator you have U13 into 12 plus U23 into 1.5, and the constraint exactly remains the same. Now the question obviously, as we have already discussed, is that in the conceptual framework that we need to basically convert this objective functions for 1 to 3 or considering these 3 optimization problems 1 to 3 into a linear case. So, this is what we do. In the first case we will remove the denominator and put the denominator as 1. So, obviously it will be as this. So, what is the objective function? Objective function was initially was the ratio of output to input. So, our input is removed, put into the constraint. So, hence it will be maximization of V11 into 100. What happens to the input the constraints? So, you have basically you are taking the denominator onto the right hand side because it less than type and then again bring it to the left hand side. So, now you have a linear problem which is V11 into 100 and minus the time which is basically the case for the objective function is because for the constraints you are taking the denominator onto the right hand side, which I am just repeating, bring it to the right hand side. So, it becomes V11 into 100 minus U11 into 10 plus U21 into 2 less than 0. Similarly, you do for the second one, for the third one. And an extra constraint which comes, which I thought I will basically mention it when we are doing the formulation, is that the denominator which you had for the objective function for the first DMU now basically comes as an added constraint in the first optimization problem, and you will basically repeat it doing for the second DMU and the third DMU. So, with this I will end this 15th lecture, which is the third week of classes over, and continue discussing more of the DA part here and then later on go into solving the DA problems. Have a nice day and thank you very much.